Post-quantum cryptography. This refers to the idea of cryptographic functions that are safe against quantum processors. A quantum processor has the capability of computing all the possible answers within a defined domain. And our cryptography algorithms all have a finite number of domain answers. Many existing public key algorithms have this box that the results can fit into. And a quantum computer can easily create collapsed answers that find the exact result to break the code. The way I think of a quantum processor and how it works is it's able to align a lot of emitting events. Across the array of emitting events, we have waves that interfere with each other. And at the end results, you'll have the ability to find the one that has the highest level of amplitude. And that's the answer. It gives you the answer in that respect because it's able to calculate all of these various possibilities, which are all the possibilities in the domain. It can basically collapse on an answer within milliseconds. Quantum proof, quantum safe, and quantum resistant are the concept of algorithms that can be difficult or impossible for a quantum processor to use a cryptanalytic attack to find an answer, find a result, or crack the code. I did find it interesting that within a cryptographic quantum processor cracking scenario, only the public key algorithms that are usually asymmetric key, where you've got two key pairs, are the ones that are at risk. That makes a lot of sense to me because when you're in a symmetric key cryptography scenario, that means there's one private super secret key that you share with nobody in the world, except for the one that you want to have decrypted on the other side. And so without any sort of foundation of reference that you would get with a public key cryptography, much more difficult to get at the answer. So in this case, we need to worry about public key cryptography, which is an asymmetric cryptographic algorithm. And there are three kinds. We have integer factorization, which is the decomposition of a positive integer into product of integers. Every positive integer greater than 1 is either the product of two or more integer factors. And we either get a composite number or a prime number. We also have discrete logarithm and elliptic curve discrete logarithm. Just a little bit of extra elliptic curve on top of that. Okay, so elliptic curve is just like a nice little bonus for the discrete logarithm, where it's an approach. Let's say, okay, so we got a public key cryptography based on algebraic structure of elliptic curves over finite fields, which allows smaller keys compared to non-ECC cryptography. Okay, so all of these algorithms today, of these three, are all easily solvable with Shor's algorithm, which is an algorithm for a quantum algorithm, for finding prime factors of an integer. So once we have a quantum processor that's fast enough, or basically has enough, it needs enough bits, qubits, right, to be able to operate Shor's algorithm, it can easily find the majority of the solutions, breaking the code from any of these existing public key algorithms. Post-quantum cryptography, do we have to worry about it? A computer can break your password in no time. That sounds scary. Currently, quantum computers lack the capacity and a sufficient amount of capability to crack any existing algorithms. Well, we are on the way. It's approaching. Time's approaching. Oh, and it's still, check this out. Cryptographers are designating the new algorithms to be prepared. They call this Q-Day, the day when current algorithms will be vulnerable to quantum attacks. Part of the challenge is, even though as we're approaching more and faster, better quantum processors, everyone's still using the quantum vulnerable algorithms. That's kind of scary. We're gonna have to migrate all of our existing algorithms, and it might be challenging for us to do that. I mean, think about it. Every tech company, every bank, anything to do with the internet, they're all relying on these existing cryptographic algorithms that are vulnerable to a sufficiently powerful quantum processor. There is a slight reprieve. Check this out. That in contrast with the threat of quantum computing, mostly targeted at public key algorithms, the good news is that symmetric cryptographic algorithms and hash functions are considered to be relatively secure. This is kind of heartwarming. Hash functions are very often related to being able to capture password credentials but not storing them directly in a database. From a security perspective, most login-based systems leverage this technique, which means they're already pretty much quantum secure. So your password, we don't have to worry too much about your password at this time, even some years in the future when quantum processors get fast enough. Quantum processors exist today, and one of the challenges that they bring around the table is security. From a security perspective, guess what? They are powerful enough to break some common cryptographic algorithms. A lot of our algorithms today are based on factoring large numbers, and we can see where we're at today by giving it a try with existing compute capability. You can have a quantum processor in your fingertips, accessing them in a cloud environment. So take, for example, RSA, which is a cryptographic algorithm based on the difficulty of factoring large integers. It's considered NP hard. Basically, at a sufficient bit depth, it's basically impossible for existing computer processors to solve those or crack the code. However, with a quantum processor and Shor's algorithm, leverage the polynomial, the equations on a quantum computer. Even though we're a little ways away from doing large numbers on a quantum computer, we still can factorize integers of a pretty decent size. And this is a really good, so with D-Wave and other quantum processors, they do offer you a polynomial interface through quadratic unconstrained binary optimization. QUBO, which allows you to set up and pair up a coefficient and other variants alongside of every single one of the waves that are going to be emitted during the processor's burst, like burst moments, right? So when you set up your QUBO, you can set up coefficients in such a way that match up with Shor's algorithm. You can burst or emit all the waves and find the collapsing point, which will give you the exact answer you're looking for in factorizing integers. So with 94 qubits, we can get something that looks like an integer factorized of 376,000, which is kind of small. And I think with 94 qubits, you should be able to do a lot bigger numbers than that. It's possible that the problem is the coefficients have some sort of range here. Could there be, I guess there could be a resolution limit based on the sensors on the output when the waves are collapsed. So in Shor's polynomials, when you're assigning coefficients, even with 94 qubits, you only have so much room. Ooh, but what's interesting here is using D-Wave's hybrid approach, where they sort of merge some of the quantum and classical using QUBOSOLVE. They could factorize numbers just slightly over 1 million with only 89 qubits. So what I would like to see a graph that shows per qubit that's added into the processor how big those maximum factorized numbers could be, because then we'll find the tipping point. And then we're looking at IBM's Q System 1, which can factor 10-bit integers, which is not that big. That's like what is that, 1,000? That's a very small number. Oh, okay. D-Wave can do, 1,000-fold. That's a huge number difference. This shows that D-Wave is ahead, right? But this was all almost 4 years ago. Where are we today? Okay. I just did Google. 433 quantum bits. Okay, that's quite a bit. That means we have quite a bit more power in these quantum processors. So still, I feel like that should be enough, but I'm hearing it is not the case yet. It's not the case to be worried about it, but if we're hitting these numbers, we're starting to get close. How many qubits do we need to crack the RSA? An RSA cipher that's 1024 bits. This will tell us how soon we have to worry about quantum being able to break cryptography. Are we in the danger zone yet? Will quantum processors break existing cryptographic algorithms? A quick look at the math says no. It's going to take a little while, because I'm taking a look at the algorithms here. They even mentioned the most resource efficient method using Shor's algorithm, polynomial coefficients, which we can take advantage of a quantum processor using quadratic unconstrained binary optimization, which is an algorithm that allows you to generate a polynomial to submit to the processor, the coprocessor, the quantum CPU, where you can assign coefficients for each qubit and emit an event, right? So you can emit the waves, and the interference will give you the result of the factorization using Shor's algorithm. In order to factorize these numbers, we see it's possible with 94 logical qubits. We can factorize this number here fairly straightforward, which is 376,000. And I was super curious to see when we scale up the number of qubits, how big is the number? Because this number, in order to get an RSA 1024-bit, we need something that's going to allow us to solve for a number that's 300 digits long, right? This is only 6 digits. 1, 2, 3, 4, 5, 6. But to get to the RSA level, where it's a 1024-bit, that's a number that is, in the 300 digits range. So we need a few more logical qubits. So here's a rough graph of what that looks like. The y-axis is qubits, and n is the integer, which is just that we're going to be factorizing. And as n gets bigger, we get a bigger n, we need more qubits in order to solve it. So we need about 3 qubits in order to solve an integer to the size of 50. Factorize it. What are the factors? So if we zoom out, gotta zoom here, zoom quite a bit. We have to zoom quite a bit before we can get, because look, right here, here's an example. This is an example RSA number, or 1024 bits, is about this. This is a very big number. This very big number right there. I don't know how you would go about saying what that number is. Trillion, some very large number. So we need our exponent to be the power of 300. And I've been zooming for a while, and it's only at 13 here. So we're nowhere near even a hundredth of where we need to be just in terms of my zooming, and we already need 400 qubits to solve a number that's not even close to what RSA is offering, even at 1024 bits. So 400 qubits is not enough. And today we have an IBM processor that is around above 400 qubits, and that's our current number. Okay, I was trying to get the x-axis to go out that big, and it wouldn't. It had a problem. The graph, it hit its limits. So in order to get close, we need somewhere around the range of 80 to 100,000 qubits to break RSA. That's what I'm looking at. Around 80 to 100,000 qubits to break 1024-bit RSA. So let's say 100,000. Let's just round up, say 100,000. You probably could make improvements on the algorithm and it would be lower than that, but let's say 100,000 qubits. And then we can crack numbers that are this big, which are very big numbers. So if we need 100,000 qubits and we're currently at 433 qubits, there's a ways to go. We've got a little ways to go. So we're a decade plus. At least, are we looking at 10, maybe 5, but probably 10 to 20 years? Depends. We need some sort of breakthrough to increase the density of qubits. Post-quantum cryptography, are we safe? Is there a solution available that allows us to create a secure cryptographic algorithm with public key cryptography that is quantum proof, or at the very least quantum resistant, that we can continue to increase the bit depth? The answer is yes. However, according to our America's Cyber Defense Agency, there's a plan. We got a plan. And the answer is that we're going to create a desired and recommended algorithm for commercial products in 2024. So that's very soon. We're basically there. So we'll start seeing some recommended algorithms that are quantum proof. The good news is this is only most basically is going to be for public key cryptography, for asymmetric key pairs where you've got a public key and a private key. Those are the ones that are at risk of quantum cracking. So things like hashing algorithms like SHA-1, SHA-256, which are used for signing and storing signatures in a database which represent a password. You would be able to store the signature of a password without having to store the password itself. Those things we're actually okay with, because typically it's one way, or it requires, with symmetric key cryptography, it's a cipher with there's a secret, so there's nothing to grasp onto. Like with a public key, you have a starting point. Symmetric key cryptography, we only have one key, and that key is always secret. So the good news is we have, through the CISA, they're going to be recommending us in 2024 some post-quantum cryptographic algorithms that we can take advantage of, that we need to in order to protect against these quantum processors. Even though it's a little while away, we're looking, in order to crack the 300-digit number, which is RSA, we're going to have the 1024-bit, right? That's 300 digits. We need a quantum processor with around 100,000 qubits. And today we only have around 433 qubits. So not to be worried yet, but pretty soon we're going to need to worry within the decade. So it looks like we should be checking this out. For anything that you leverage in terms of public key cryptography, this is where we need to pay attention. Even taking a look at the roadmap from DHS, they are describing that we need to start taking a look at the future, assessing our risk, and specifically focusing on the public key cryptography being used for those systems. We need to identify those. And then once we have the information around what's the next step, we have to plan for a transition. DHS does recommend that we prioritize our systems based on the sensitivity of data that's stored in the cryptographic stores. Each of them, for example, if they're password or root keys, then that should make it to the top of the list. So this is just something that we keep in the back of our minds that we do need to pay attention to. However, we are a ways out. 2024 is the year where they will be providing us some recommendations for the algorithms that are quantum resistant or quantum proof. On Wikipedia, we have a list of algorithms here that represent some of these options that we're considering. So very likely we'll see one of these variants be recommended. Look looking at these key sizes. This is a big key right here, 1 megabyte with the GOPA-based Michaelis. So yeah, there's even better news. We have candidate algorithms that are quantum proof or quantum resistant, and we have a long time and a long roadmap to be able to implement those.